Hello and welcome to the GameWise. I'm so glad you've joined me tonight, as the world outside begins to hush, as the day's vibrant chorus of traffic and work and life fades into a gentle, muted hum, and the stars, one by one, ever so slowly begin to wink into view. We're going to embark on a very gentle journey together. Take a moment to truly feel the space you're in right now. Feel the weight of the blanket over you, a gentle pressure that brings a sense of security and peace. Notice the softness of the pillow as it cradles your head. Feel the quiet rhythm of your own breath, a gentle, effortless tide flowing in and out, a constant, soothing anchor in this present moment. Our purpose tonight is to explore a truly fascinating question, one that has puzzled thinkers and inspired dreamers for generations. Can we do time travel at the speed of light? It's a concept plucked right from the pages of our most imaginative stories, a whisper of glorious possibility that tickles the very edges of what we know, and yet it rests on the very real, very curious laws of our magnificent universe. We are so often drawn to this idea of navigating time, aren't we? Perhaps it's a deep-seated longing to revisit a cherished memory, to feel the warmth of a moment one more time, or maybe it's a desire to undo a regret, to choose a different path. Or perhaps it's simply a profound and pure curiosity to glimpse the world that is yet to be, to understand our place in the long unfolding story of existence. This fascination speaks to our deep and intimate connection with the flow of moments that make up the rivers of our lives. Now, I do have a lighthearted warning for you, a gentle disclaimer before we begin. I truly hope that the wonders we are about to explore tonight aren't so interesting, so utterly captivating, that they keep you wide-eyed and alert, your mind buzzing with cosmic questions long into the night. My deepest wish, my truest intention, is that as we wander together through these ideas, much like walking through a quiet, mystical, moonlit garden, your eyelids will grow heavy, your mind will drift and float, and you'll find yourself gently, peacefully falling into a deep and wonderfully restorative slumber. Before we settle into our quiet exploration, if you find yourself enjoying this cozy and curious corner of the internet, this little sanctuary of sleepy science, I'd be truly delighted if you considered giving this video a like and perhaps subscribing. It helps our little community grow, and I love seeing how far our sleepy science travels. It feels as if we're all connected by a shared, quiet sense of wonder. And speaking of travel, I'm always so curious to know where in the world you are listening from and what time it is as you begin to drift off. Please feel free to share that in the comments if you feel so inclined. It truly warms my heart to picture you in your own quiet space in your own time zone. I love to imagine the quiet glow of screens in darkened rooms, from midnight in Melbourne to evening in Edinburgh, all of us joining together on this gentle journey. It's a beautiful and comforting thought, seeing how far our sleepy science whispers can reach across the globe, connecting us all. Now, let's settle in even deeper. Let your breath slow down even more, to the pace of a gentle, lapping wave on a tranquil, moonlit shore. Feel the day's thoughts, its busy worries, and its endless to-do lists float gently away from you. Imagine them as little paper boats being carried away on that slow-moving stream, disappearing from sight. There is absolutely no rush here, no test to pass, no need to grasp every single detail. Just allow the ideas to wash over you, like a comforting, warm current carrying you out to a sea of tranquility. And as always, please remember, the concepts we discuss are purely for exploration and for wonder. This content isn't medical advice, nor is it a rigorous academic lecture. It's just a gentle whisper from the cosmos, a soft scientific lullaby composed from the laws of physics designed to help you unwind, relax, and dream. Imagine, if you will, that time is like a vast, invisible river. For most of human history, this is how we've pictured it. We've imagined ourselves as tiny boats, or perhaps leaves, all floating on this one great river, perpetually flowing downstream together. From the misty, half-forgotten upstream of the past, through the immediate and tangible moment of the present, and into the unseen, mysterious downstream of the future. But what if this river isn't quite as simple as it seems? What if it's not a single, straight channel? What if its currents can twist and turn upon themselves? What if there are eddies where the flow is slow and circular and rapids where it rushes ahead? And what if the river can even slow down, its current becoming thick and syrupy? For some boats, more than others. For centuries, we perceived time as an unyielding, universal constant, a steady, metronomic tick-tock that marches forward for everyone, everywhere, at the exact same pace. This was the view of the brilliant mind of Sir Isaac Newton, who saw time as an absolute, unchanging backdrop, like the fixed stage upon which the grand play of the universe unfolded. It was, in his view, like a master clock, hanging invisibly in the cosmos, ticking with perfect uniformity for every atom, every planet, and every distant galaxy. A reliable, predictable, universal beat. But as our tools for observing the universe became more sophisticated, as we began to build clocks of astonishing precision and telescopes that could peer into the deepest reaches of space, we discovered that time, this seemingly immutable river, holds secrets far more profound, far more personal than we ever imagined. It's not just a backdrop, it's intricately, dynamically woven into the very fabric of existence, a pliable thread in the grand tapestry of reality. So as you drift in your own quiet space, consider this. Is time merely a measurement of change, an invention we use to mark the sequence of events, like the hands on a clock? Or is it a fundamental dimension, as real and as pliable as the three dimensions of space that you occupy? The answer, as we shall gently uncover, is far more wondrous and strange than we might first imagine. To understand the possibility of travel through time, we must first think more deeply about travel through space. Think for a moment of a tiny ant scurrying across a vast picnic blanket. To the ant, this is a grand adventure, a journey at a tremendous speed across a seemingly endless patterned plane. To us, however, observing from our great height, it's rather slow, a leisurely and meandering stroll. Our perception of speed is entirely relative. Speed, as we usually think of it, is simply how much distance you cover in a given amount of time. Miles per hour, kilometers per second. It seems so simple and straightforward, doesn't it? But in the vastness of the cosmos, what does fast truly signify? Is there a universal speedometer, a cosmic speed limit that nothing, absolutely nothing, can ever truly exceed? And if there is such a limit, what does it imply for everything else in the universe? Imagine yourself trying to run faster and faster, pushing yourself with all your might. At some point, your body simply won't go any quicker. There is a physical limit. The universe, in its elegant and silent wisdom, has a similar but far more fundamental and unshakable speed limit. But this limit isn't just a number on a dial. It's a fundamental characteristic of the structure of reality itself. It's a bit like the speed of sound here on Earth. No matter how loudly you shout, no matter how powerful your voice, that sound cannot travel faster than the air itself will allow it to propagate. The medium dictates the speed. In the vacuum of space, for light, this limit is far more profound and far more mysterious because light needs no medium. It sets its own speed limit. Now let's turn our gentle gaze to light itself, that ephemeral, beautiful dance of particles and waves that illuminates our world and our understanding. Imagine yourself floating weightlessly in the quiet, inky blackness of deep space, holding a simple flashlight. You press the button, and a brilliant beam of pure light shoots out, painting a straight path in the endless darkness. Now imagine you're on a futuristic spaceship, a sleek vessel that is hurtling through the cosmic void at an incredible speed, perhaps half the speed of light itself. You go to the forward viewport of your ship, and you shine that very same flashlight forward, out into the cosmos. What do you see? Intuitively, you might expect the light to travel even faster from your perspective, because surely you have added your spaceship's considerable speed to the light's own inherent speed. It's like throwing a ball forward from a moving car. The ball's speed relative to the ground is the speed of the car plus the speed of your throw. It makes perfect sense. But here's where the universe whispers its most astonishing, most profound, and most counterintuitive secret. The light still travels away from you, the astronaut on the fast-moving ship, at the exact same speed. The cosmic speed limit, which we call c. This isn't just a very, very fast speed. It's a fundamental constant of the universe. It doesn't matter if you're standing still on a quiet planet or moving at an unimaginable velocity on a starship. It doesn't matter if you're moving towards the source of light or away from it. Light in a vacuum always travels at precisely the same speed to any and all observers, approximately 299,792,458 meters per second. This unwavering, stubborn, and absolute speed, this universal constant, is the bedrock upon which so much of our modern understanding of time and space is built. It's as if the universe has a single, inviolable law, and light is its perfect, unwavering enforcer. This deeply peculiar and non-negotiable nature of light is the first gentle hint, the first crucial clue that our everyday intuitive understanding of time might be beautifully, wonderfully, and gloriously incomplete. If light always travels at the same speed for everyone, no matter how fast they are moving, then something else in our equations of reality has to give. The cosmic equation of motion must balance itself out somehow. So let's imagine two identical, perfectly crafted clocks. Perhaps they are beautiful grandfather clocks with ornate pendulums swinging in perfect harmony. One of these clocks is resting gently beside you in your room, its familiar ticks and talks a soothing, steady rhythm in the quiet air. It is a comforting sound. The other, identical clock is placed aboard a rocket ship, a futuristic vessel that zips past you at an incredible speed, a velocity that gets closer and closer and closer to the speed of light. From your perspective, as you stand still and watch that spaceship speed away into the blackness, the clock on board appears to be ticking more slowly. Its pendulum seems to take a longer, more languid path on each swing. Its second hand seems to take a longer, more drawn-out path around the clock's face. This isn't just an illusion. It's not a trick of the light or of perspective. It is a real, measurable physical phenomenon called time dilation. It's as if time itself, the river of existence, is stretching and slowing down for the moving clock. The faster that rocket ship goes, the slower its clock appears to tick when compared to your own stationary clock. This is one of the most profound and mind-bending predictions of Albert Einstein's theory of special relativity, which he unveiled to a stunned and disbelieving world over a century ago. It suggests that time isn't a universal, unyielding rhythm. It's not a single river. It's more like a personal, relative experience, intimately and forever linked to your own personal motion through space. It's like listening to two identical, beautiful songs played by two identical musicians. But one of the musicians is playing their instrument while skating past you on ice. To you, their song would sound slightly lower in pitch and slower in tempo, its notes drawn out and elongated, simply because the player is moving quickly. Can you feel that gentle imaginary stretch of time, that slowing of the cosmic rhythm, even as you lie perfectly still and peaceful in your bed? This idea of time slowing down, of identical clocks falling out of sync simply due to motion, might sound like something purely from a fantastical science fiction novel, doesn't it? It feels far too strange to be part of our real world. It goes against all our everyday intuition. But the universe, in its quiet and elegant way, provides us with subtle yet absolutely unmistakable proofs of this strange reality every single day. Let's consider for a moment the strange case of some tiny fleeting particles called muons. They are like very short-lived, heavy cousins of electrons, and they are born high up in the Earth's atmosphere, many kilometers above our heads. They spring into existence when cosmic rays, which are energetic, charged particles that are always raining down on us from the depths of outer space, from exploded stars and distant galaxies, collide violently with the molecules of air in our upper atmosphere. Muons are notoriously incredibly short-lived. They decay or fall apart into other, more stable particles in just a tiny fraction of a second, about 2.2 microseconds to be a little more precise. A microsecond is a millionth of a second. If time flowed universally for these muons, just as it does for us in our relatively stationary world on the ground, they would not have nearly enough time to travel all the way down from the upper atmosphere to reach the sensitive detectors we have placed on the Earth's surface. Their incredibly short lifespan would mean they'd decay long before completing their journey. They could only travel about 660 meters before vanishing, and yet they do arrive. We detect them constantly, a steady patter of cosmic rain. Many of them successfully make it all the way to the ground. This is because, from our perspective on Earth, these muons are traveling at incredibly high speeds, very close to the speed of light, at over 99% of c. And because they're moving so fast, their own internal clocks, their very experience of the passage of time, slows down dramatically. So for them, in their own fast-moving reference frame, very little time actually passes during their plummet to Earth. This allows them to complete their long journey down to us before their short lives are over. It's as if they are granted a much longer life, a life stretched out from our point of view simply because of their incredible speed. This beautiful and subtle cosmic evidence perfectly confirms that time dilation isn't just a theoretical curiosity. It's a verified constant dance of particles happening in our sky right now above your head. Now, if the universe adjusts time to protect the constancy of light speed, it makes a certain kind of intuitive sense that it might adjust space as well. Just as time can stretch and slow down, space itself can compress and shorten when you move at these extreme speeds. Let's imagine that same sleek rocket ship again, still zipping past you at a velocity tantalizingly close to the speed of light. Not only does its clock appear to tick more slowly to you, but from your stationary perspective, the spaceship itself appears to have shrunk, to have become shorter, but only and specifically in the direction of its motion. This equally strange and wonderful phenomenon is called length contraction. The faster the ship goes, the shorter and more compressed it looks to you, the outside stationary observer. It's like taking a perfectly ordinary ruler, a familiar meter stick, and holding it flat on a table. It has a definite length, but if you were to somehow be able to push that ruler to near light speed, while you remain still, it would appear to you to become shorter and shorter and shorter along its direction of travel, as if space itself were being squeezed in that direction. Of course, if you were an astronaut on that spaceship floating alongside the ruler, you wouldn't notice any change at all. To you, your clock would seem to tick perfectly normally, the spaceship would seem to be its usual comfortable size, and your meter stick would still, of course, measure exactly 1 meter. It is only the external stationary observer who perceives these fascinating distortions of space and time. This beautiful, intricate, and inseparable intertwining of space and time, where one dimension can contract as the other dilates, reveals that they are not separate entities at all, but rather two facets of the same cosmic diamond. They are forever linked within a single, unified, four-dimensional fabric that we now call space-time. Think of this fabric of space-time as a grand cosmic tapestry. 3 of the dimensions of this tapestry are the familiar dimensions of space we move through every day, up and down, left and right, forward and backward. The 4th dimension is time, the thread that runs through it all, carrying everything forward from the past into the future. When you are sitting or lying perfectly still, as you are now, you are traveling purely through the time dimension at the maximum possible speed, 1 second per second. But the moment you begin to move through space, you have to borrow some of your speed from the time dimension. The universe demands this trade-off. The faster you travel through the 3 dimensions of space, the slower you must therefore travel through the 4th dimension of time. This is to ensure that your total combined speed through this 4-dimensional fabric of space-time always and for everything equals the speed of light. It's a wondrous and deeply elegant concept. We are all always traveling through space-time at the speed of light. It's just that for most of us, resting here on Earth, almost all of that travel is through the dimension of time. Only when we start moving very, very fast through space do we begin to notice the trade-off, as our personal journey through time begins to perceptibly slow down. Now, let's consider yet another intriguing consequence of trying to move ever closer to that ultimate cosmic speed of light, the concept of mass. Imagine you're trying to push a tiny, smooth pebble across a polished floor. At first, it's easy to get it moving, requiring only a gentle nudge. But what if that pebble suddenly felt heavier and heavier and heavier the faster it moved? What if it resisted your push more and more, the closer it got to a certain speed? This is precisely what happens with objects that have mass when they approach the speed of light. As something with mass gains speed, its relativistic mass, which is really a way of talking about its inertia, its resistance to being accelerated further, appears to increase from an outsider's perspective. It becomes progressively harder and harder to accelerate it, requiring more and more energy for each tiny incremental increase in its speed. Think of it like trying to row a small boat upstream against a powerful current that gets stronger and stronger the faster you try to row. The faster you attempt to go, the more powerful the resistance you feel, and the more energy you must expend for each foot forward, as if the boat itself were magically becoming heavier and more sluggish in the water. If an object with mass, any mass at all, were to somehow reach the speed of light, its relativistic mass would become infinite, and would therefore require an infinite amount of energy to accelerate it to that point. This is why only massless particles, like the photons that make up light itself, can travel at the speed of light. For anything with even a tiny whisper of mass, from the smallest electron to the largest, most majestic galaxy, this cosmic speed limit acts as an impenetrable yet deeply elegant barrier. It's a gentle but firm rule from the universe, a silent gatekeeper of its most fundamental laws, ensuring the stability and predictability of the cosmos. If everything with mass experiences these strange and wonderful effects as it approaches the speed of light, what about light itself? What is time like for a photon, a single, tiny particle of light that always travels at the cosmic speed limit? This is where our gentle journey into wonder takes an even more ethereal and beautiful turn. Let your mind drift into this abstract space. From a photon's own perspective, from its own strange point of view, its entire journey is instantaneous. Imagine a single photon being born in the nuclear furnace of the surface of our sun. It is emitted and it begins a journey, traveling across the vast, cold, empty expanse of 93 million miles of space to eventually reach your eye, perhaps as you sit by a window. For us, here on Earth, that journey takes a little over 8 minutes. We can time it, we can measure it with our clocks, but for the photon itself, it's as if no time has passed at all. In the photon's frame of reference, it is emitted, and in the very same moment, with absolutely no duration in between, it is absorbed. The immense distance it covers is, for it, length contracted all the way down to zero. A photon does not age. It does not experience a past, a present, or a future. It does not experience a temporal dimension as we do. It exists in a state of pure is. It's like stepping through a magical doorway and instantly being on the other side with no memory or experience of the room you walk through. This profound and beautiful concept suggests that for light, time simply doesn't exist in the way we understand it. It's a timeless traveler, a pure surge of energy experiencing its entire cosmic voyage in literally no time. So, if we could somehow ride a beam of light, would we be time traveling? In a very strange and absolute sense, yes. We would be traveling to the ultimate extreme of time's passage. No time at all, an instant jump to our destination. So, we now understand that nothing with mass can ever truly reach the speed of light. That infinite mass and the infinite energy it would require makes it a physical impossibility. It's the universe's ultimate and most democratic speed limit. But what if we could get very, very close? Let's imagine a magnificent, futuristic spacecraft, a vessel of polished metal and glowing lights, powered by some unimaginable future technology, perhaps harnessing the energy of stars. This ship is capable of accelerating to 99.9999999% of the speed of light. For the brave and adventurous astronauts on board this incredible ship, time would slow down so dramatically that it would beggar belief when compared to the passage of time for those of us left behind on our gently spinning home world, Earth. A journey to a nearby star system, like Alpha Centauri, which is about 4 light years away. A trip that might take, from our perspective, just over 4 years, could for them, on their ship, feel like only a few days or weeks. If they were to travel to the center of our galaxy, a journey of 25,000 light years, and then return, 50,000 years would have passed on Earth. Civilizations could rise and fall, but for the astronauts, only a few decades of their own lives would have passed. When they returned, they would find that everyone they had ever known was long gone. That the world they had left was a part of ancient history. This is, in a very real and physical sense, a form of one-way time travel into the future. They would effectively be skipping ahead in time relative to the rest of us. However, as we've seen, the energy requirements to achieve such speeds are truly astronomical, far, far beyond anything we can currently conceive. It's like trying to accelerate a great mountain range to the speed of a rifle bullet. The energy needed becomes mind-bogglingly, almost infinitely immense. So even if we could one day overcome the incredible engineering challenges, the universe itself, with its elegant and unbending laws, gently reminds us that the absolute speed of light remains an unreachable sacred horizon for anything with even a whisper of mass. Let's linger for a moment more on this poetic idea of an unreachable horizon. Think of a gentle, wide river flowing steadily towards a colossal, thundering waterfall. A leaf floating on the water's surface can get closer and closer and closer to the edge. It can drift right up to the point where the water begins to curve downwards. But once it goes over that edge, it cannot return upstream. It has crossed a point of no return. The speed of light acts as a similar, yet far more fundamental and absolute kind of boundary in our universe. For any object that has mass, no matter how tiny, trying to reach the speed of light is akin to trying to cross an impossible event horizon. As an object accelerates and gets closer to C, more and more of the energy you put into it goes into increasing its apparent mass, its inertia, rather than increasing its speed. It's like trying to fill a balloon that becomes infinitely more resistant to expansion the fuller it gets. You can keep pushing energy in, but you get less and less actual speed in return as you approach the limit. The very fabric of spacetime, as so beautifully described by Einstein's mathematics, creates this cosmic speed limit. It is not, it's important to remember, a technological limitation that we might one day overcome with a better engine or a cleverer design. It is a fundamental and deep property of reality itself. We are forever, it seems, bound to travel at speeds less than light through space. This beautiful inherent limit is what ensures the consistency of physical laws of cause and effect across the entire universe. It's a gentle, cosmic reminder that while we can dream of reaching for the stars at incredible speeds, there is a boundary, a horizon, beyond which only pure, massless light itself can venture. Our gentle journey now takes a slight turn, a subtle shift in perspective. We drift from the effects of high-speed motion to the very nature of the universe's most pervasive force, gravity. Imagine once more that you have a large, soft, black rubber sheet stretched out tightly and perfectly flat, like a cosmic trampoline. Now, you gently place a heavy bowling ball in the center of the sheet. The weight of the ball creates a dip, a deep, sagging curve in the fabric of the sheet. The sheet is no longer flat. Now, if you gently roll a small, lightweight marble nearby, it won't travel in a perfectly straight line as it would on a flat surface. Instead, its path will be deflected. It will curve inward, drawn by the depression made by the heavy bowling ball. It follows the curve. This simple, tangible image helps us to begin to understand Albert Einstein's revolutionary general theory of relativity. He revealed to the world that gravity isn't a mysterious, invisible force that pulls things together from a distance. Instead, gravity is the curvature of space-time itself, a curvature that is caused by the presence of mass and energy. Massive objects like our own dear Earth or our sun or a distant giant star create these dips or warps in this invisible cosmic fabric. The marble, rolling on the sheet, doesn't feel a pull from the bowling ball. It simply follows the straightest possible path through the curved space. And just as space is warped by mass, so too, inextricably, is time. The stronger the gravitational field, the more space-time is curved, and the slower time itself passes for an observer within that field. It's like the gentle slowing of a beautiful melody when you stretch the very strings of the violin it's being played on. Time is not only affected by how fast you move, but also by how close you are to a massive object. So even now, the immense but gentle gravity of the Earth is warping time for you, causing your clock to tick just a tiny, tiny fraction of a second slower than it would for a satellite high above. If the gentle gravity of Earth can warp time, then what happens near the most extreme, most voracious gravitational giants in the entire universe? The mysterious and awesome black holes. Let's return to our rubber sheet analogy one last time. But this time, instead of a heavy bowling ball, picture placing something with near infinite density and weight, like a tiny, impossibly heavy ball bearing, onto the sheet. It would create a profoundly deep well, a puncture, a near infinite tear in the fabric from which nothing could escape. This is a simple picture of what a black hole does to the fabric of spacetime. Near a black hole, the curvature of spacetime is so extreme that time itself slows to an almost complete standstill from the perspective of a distant, safe outside observer. If you could hypothetically and safely hover at a distance and watch someone fall towards a black hole, you would see them appear to slow down as they approached the edge, their movements becoming agonizingly sluggish. Their light would become redder and dimmer, and eventually they would seem to freeze entirely at the event horizon, the invisible point of no return. Their clock, from your distant vantage point, would seem to have stopped ticking completely, frozen for all eternity. For the person actually falling in, however, time would still seem to flow perfectly normally from their own perspective. They wouldn't notice anything unusual about their own experience of time, even as the entire future history of the external universe flashed by in their final moments. This profound, mind-bending difference in the passage of time near black holes is one of the most astonishing and verified predictions of general relativity. They are cosmic laboratories where our concept of time truly becomes fluid, stretching and distorting in ways that challenge our deepest, most cherished intuitions about reality. Now let's allow our minds to float gently away from the established and into the realm of the truly speculative, the purely theoretical, the beautifully enchanting, the idea of wormholes. Imagine you have a crisp red apple, and there's a tiny ant walking diligently on its shiny curved surface. To get from the top of the apple, where the stem is, to the very bottom, the ant has to walk all the way around the curved skin of the apple. It's a long journey. But what if you, with your three-dimensional perspective, could poke a hole directly through the center of the apple, creating a shortcut from top to bottom? That's the essential and beautiful idea of a wormhole, a hypothetical, theoretical, tunnel-like structure that could, in principle, connect two very distant points in space-time. These cosmic shortcuts, sometimes called Einstein-Rosen bridges in the language of physics, are valid theoretical solutions that arise from the complex mathematics of Einstein's equations of general relativity. If traversable wormholes could exist, they might not only allow for a form of faster-than-light travel through space, not by breaking the speed limit, but by simply cheating the distance and taking a shortcut, but also, in theory, enable time travel. By taking one mouth of a wormhole and moving it at near light speed for a while, or by placing it for some time near a very strong gravitational source like a black hole, a time difference could be created between its two mouths. This would mean that stepping through one end of the wormhole could lead you to a different point in time at the other end, potentially sending you into either the future or the past. However, and this is a very important however, it is so important to remember that these are highly, highly theoretical constructs. To keep them open and stable enough for anything to pass through, they would require a form of truly exotic matter that has a kind of negative energy or negative pressure, something we have never ever observed in the universe and aren't even sure can exist according to the known laws of physics. But it's a beautiful idea to ponder as you drift off into sleep, isn't it? A dream of cosmic shortcuts, of folding the grand four-dimensional tapestry of existence to bring two distant points, or two distant times, together. If time travel into the past were ever to become a reality, it immediately raises a whole host of fascinating and sometimes deeply unsettling philosophical questions and logical paradoxes. The most famous and widely discussed of these, which has been the subject of countless stories, films, and sleepless nights, is the grandfather paradox. Imagine you have successfully built a time machine. You step inside, you pull the levers, and you travel back in time to the era when your grandfather was still a young, unmarried man, long before he had ever met your grandmother. And then, through some clumsy accident, you cause an event that prevents your own grandfather from ever meeting your grandmother. If that were to happen, one of your parents would never have been conceived, and therefore neither would you. But if you were never born, then how could you have possibly grown up to become a brilliant inventor, build a time machine, and travel back in time to cause the accident in the first place? It's a tangled, maddening, logical knot of cause and effect, isn't it? Another similar puzzle is the bootstrap paradox. Imagine an aspiring playwright is struggling with writer's block. A time traveler from the future appears and hands him a beautiful, bound book containing the complete works of William Shakespeare. The playwright, Amazed simply copies the plays and publishes them under his own name, becoming the famous Shakespeare we know. The plays are celebrated for centuries until one day a future time traveler takes a copy of them back in time to give to that struggling playwright. The question is, where did the plays originate? They seem to have no point of creation. These paradoxes highlight the profound challenges that backward time travel presents. While physics allows for one-way time travel into the future through time dilation, traveling into the past is far more problematic, often leading to these seemingly unbreakable causal inconsistencies. Some theories propose ways around these paradoxes, such as the idea of parallel universes or alternate timelines, where your actions simply create a new branch of reality. Or perhaps the universe has a fundamental self-consistency principle, a kind of cosmic law that would ensure that events would always conspire to prevent you from ever creating a true paradox. But for now, they remain intriguing thought experiments, gentle reminders of the delicate and intricate dance of cause and consequence that governs the flow of our universe. As we gently drift through all these heady concepts of time, have you ever stopped to wonder why it seems to flow in only one direction for us? Why do we remember the past with all its joys and sorrows, but not the future? Why does a broken glass never spontaneously reassemble itself on the floor, its shards flying back together? This inherent, seemingly unbreakable forward motion of time is often referred to as the arrow of time. And one of its most powerful and beautiful explanations comes from a profound concept in physics and chemistry called entropy. Entropy is, at its core, a measure of disorder, or randomness, or chaos. The second law of thermodynamics, which is one of the most fundamental and well-tested principles of our entire universe, tells us that in any closed, isolated system, the total amount of entropy, the total amount of disorder, will always tend to increase over time. Think of an ice cube in a glass of warm water. The ice cube is a highly ordered structure of water molecules, but it will always melt, and its molecules will disperse randomly throughout the water, increasing the overall disorder of the system. Think of your room. Left to its own devices, it naturally tends to get messier, not tidier. Order requires a constant input of effort and energy. Disorder is the natural, easy state of things. This universal, inescapable tendency towards disorder gives time its forward direction. From a grand, cosmic perspective, our universe began in a very, very low entropy state. It was a state of incredible order and simplicity shortly after the Big Bang, when everything was hot, dense, and uniform. And ever since that initial moment, it has been expanding, cooling, and becoming more disordered, forming complex structures like stars and galaxies, and moving ever forward towards a state of higher and higher entropy. So, the fundamental reason we experience time moving forward, the reason we can't unbreak that glass or unspill the milk, is tied deeply to this fundamental cosmic drive towards increasing disorder. It's a gentle, relentless current carrying everything in the universe from simplicity to exquisite, beautiful, complex disarray. Even as we explore these grand cosmic ideas of light speed and warped spacetime, please remember that you, yourself, are a time traveler too, in the most profound and immediate sense. Every moment that passes, every single breath you take, carries you forward into the future. Your own personal clock, the intricate and wonderful dance of your biological processes, from the beating of your heart to the division of your cells, is subtly, almost immeasurably, influenced by your motion and by the gentle but constant gravitational pull of the Earth. While these relativistic effects are far, far too minuscule for us to ever notice in our daily lives, they are absolutely real, and they are measurable with sufficiently precise atomic clocks. Let's consider again the delicate and incredible precision of the global positioning system, the GPS satellites that orbit high above our Earth. They are constantly moving at very high speeds, about 14,000 kilometers per hour, and they also exist in a region of slightly weaker gravity than we do down here on the surface. Because of this combination of effects, time slowing for them due to their speed, but speeding up for them due to the lower gravity, their clocks actually tick just a tiny bit faster than clocks on the ground by about 38 microseconds every single day. If scientists didn't constantly account for and correct for these tiny relativistic effects, our GPS systems would fail. Navigational errors would accumulate at a rate of about 10 kilometers every single day, making the system completely useless. So, as you close your eyes and feel your body at rest, perhaps you can appreciate that gentle, continuous, and inevitable drift into tomorrow. You are a passenger on a great ship called Earth, on a journey through space-time, constantly moving, constantly aging, constantly experiencing the silent, beautiful unfolding of moments, a quiet and living testament to the universe's incredible hidden precision. Now let's pull back our perspective one last time, zooming out to consider time on the grandest, most majestic scale imaginable. The universe itself has a story, an epic and sweeping narrative that stretches back some 13.8 billion years to its very mysterious beginning. From the blazing, unimaginable intensity of the Big Bang, a point of near infinite density and heat, through the slow, patient cooling and formation of the first elementary particles and the first simple atoms, through the gravitational gathering of cosmic dust and gas into the first fiery stars and nascent galaxies, and eventually, after billions of years, to the emergence of life on a tiny, fragile, blue and white planet, time has been the silent conductor of this cosmic symphony. The light from the most distant galaxies we can see with our most powerful telescopes reaches us having traveled for vast expanses of time, for billions and billions of years, allowing us to effectively peer directly into the universe's distant, ancient past. When you gaze up at the clear night sky, the starlight that twinkles and reaches your eye is not from the present moment. It's a fleeting glimpse of history. The light from our closest star, Proxima Centauri, is over 4 years old. The light from the Andromeda Galaxy is over 2.5 million years old. You are seeing it as it was when early human ancestors walked the Earth. It's as if you're looking through a natural, cosmic time machine that allows you to witness moments that happened long, long before any human ever recorded history. This profound and beautiful connection between light, distance, and time reminds us that the universe is not a static, unchanging place, but a dynamic, vibrant, ever-evolving entity, with each and every photon of light that travels through it carrying with it a silent, coded whisper of its ancient and fiery origins. As our gentle journey together now nears its end, and as your mind settles into a deeper and more profound state of calm, just consider for a moment the quiet, comforting persistence of time. Whether we're talking about the incredible, mind-bending speeds of light, the deep and mysterious gravitational wells of black holes, or the subtle, inexorable march of entropy, time is always present, always flowing, always unfolding. It is not just a measurement on a clock. It is an intrinsic, fundamental part of the very reality we inhabit. It weaves its way through every atom in your body, every star in the sky, every thought in your mind, every dream you're about to have. Even as you prepare to drift completely and utterly into sleep, the gentle, ceaseless, invisible current of time is carrying you forward, minute by minute, second by silent second, into the quiet, untouched promise of a new day. There is a deep and abiding comfort to be found in this understanding, a sense of belonging to something vast, ancient, mysterious, and eternal. As the cosmic dust motes of our exploration gently settle now in the quiet chambers of your mind, let's take a final moment to softly and slowly recap the wonders we've brushed against tonight. We began our journey by questioning the very nature of time itself, wondering if it's a rigid, universal river we all float upon, or a more personal, flowing dimension that is unique to each of us. We then discovered that speed isn't just a simple measure of movement, but a gateway to extraordinary phenomena, especially when we spoke of light, the universe's ultimate, unyielding, and democratic speed limit. Remember that wondrous, strange fact that light always travels at the speed c, no matter who is observing it or how fast they are moving? This single, elegant idea led us into the mind-bending world of special relativity, where we found that time itself can actually slow down for those in motion, a beautiful phenomenon called time dilation. We saw the tangible, real-world proof of this in the fleeting yet strangely extended lives of muons, those tiny cosmic travelers whose very existence on our planet's surface is a silent, constant testament to time's incredible flexibility. We then explored how space itself can contract at high speeds, shrinking like a canvas being pulled taut, and how time and space are woven together inseparably into a single, four-dimensional fabric. We touched upon the immense and staggering energy cost of approaching this speed, how an object's mass appears to increase as it goes faster and faster, creating that impossible, infinite barrier for anything with even a shred of substance. Our thoughts then floated away to the ethereal, almost magical perspective of a single photon of light, imagining a journey where time simply ceases to exist, where the start and the end of its vast cosmic voyage are, from its own point of view, one single, instantaneous, timeless event. We contemplated the immense theoretical and practical challenges of ever truly reaching light speed for any object with mass, finding that it's a fundamental event horizon, a boundary set by the very laws of the universe itself. Then our journey took a graceful turn into the realm of gravity's gentle, silent dance as we explored Einstein's great theory of general relativity. We learned how massive objects like our own planet Earth gently yet profoundly warp the very fabric of space-time around them, causing time to pass more slowly in their presence. We considered the ultimate time warpers, the enigmatic and frightening black holes, where gravity is so intense that time slows to a near-perfect crawl, a cosmic molasses from which not even light, the swiftest thing in the universe, can escape. And for a brief, wondrous moment, we allowed ourselves to dream of the fantastical, of wormholes, those theoretical shortcuts through the cosmic fabric that might, in the wildest of mathematical dreams, allow for incredible leaps through both space and time, while still gently reminding ourselves of the profound philosophical challenges and paradoxes that traveling to the past would inevitably present to us. And finally, we settled on the comforting and beautifully simple concept of the arrow of time, understanding why time only seems to flow forward for us, a direction tied inextricably to the beautiful, inexorable march of entropy, the universe's natural and creative tendency towards a state of ever greater, more complex, delightful disorder. And through all of these wonders, we recognized our own quiet, personal, and profound journey as time travelers, with each and every moment carrying us forward, our own biological clocks subtly influenced by the grand and silent cosmos all around us. So you see, even when nothing at all seems to be happening, even as the quiet night deepens around you and the world outside finally sleeps, the universe is always engaged in a profound and silent ballet of time and space, of light and of gravity. These quiet, constant, magnificent processes are happening just beneath the surface of our awareness, a gentle, unending reminder of the intricate and breathtaking beauty that underpins our very existence. Are you curled up comfortably in bed now, perhaps with your favorite blanket pulled up close and snug around you, listening to my voice with your eyes gently closed, drifting on the soft, warm edge of sleep? I truly and deeply hope this gentle exploration has helped to lull you towards a deep and peaceful and well-deserved rest. If you've enjoyed our quiet time together tonight, please consider giving this video a like. And if you haven't already, perhaps subscribe to join our cozy and curious corner of the internet. It helps us to share these sleepy scientific whispers with more fellow dreamers all around our beautiful world. And please, if you feel like it, don't forget to share where in the world you're listening from and what time it is in your part of the world. I so love to imagine our quiet community, a network of peaceful listeners, all connected by wonder, stretching across the sleeping globe. Thank you for joining me on this gentle journey through the wonders of time and light. May your dreams be filled with cosmic possibilities and peaceful, serene, starlit skies. May your rest be deep, and may your tomorrow be bright and full of gentle moments. Until next time, sleep well and keep wondering.